This video is another in the series for Math 1073 for UTSA. Today we'll be talking about Module 4.2. So the first problem says, for the following exercises, use the remainder theorem to find the remainder. So reminder, what the remainder theorem says is that when you divide a polynomial by something of the form x minus a, then the remainder will be the same value as if you just plugged a into the dividend, okay? So if I plug 4 into that, okay, 4 to the fourth. 4 squared is 16. Square that, get 256, right? Plus 2 is 258. So that is the remainder of the remainder of that division step. If we wanted to do that through long division, that's what we would get. So if we just want the remainder, we can skip a lot of steps and use this. Another example here. Remember, the format is x minus a. So when I have x plus 5, I need to think about that as being x minus negative 5. So here, a equals negative 5. Okay, so if I plug that in to the dividend, I'll get the remainder value. So if I do 4 times negative 5 to the 5th power minus negative 5 to the 4th power plus 3 times negative 5 cubed plus 6 times negative 5 minus 2. Okay, so I'm going to try to do this without a calculator. So I know that, well, there's no 5 squared here. So 5 cubed, well, let's go ahead and do it. 5 squared is 25, right? That one's easy. 5 cubed, that is 125. 5 to the 4th, that is 625. 5 to the 5th, that is 3125. Okay. Now, of course, these are, it's a little too big. And of course, these are all negative, right? So I have to keep that in mind. If I have an odd exponent on a negative number, the result is negative, right? So negative 5 to the 5th power is negative 3125. If I multiply by 4, I get negative 12,500. Okay, minus, because of the minus right there, of course, negative 5 to the 4th power will be positive 625. Okay, minus negative 5 to the 3rd power would be negative 125 times 3 is negative 375. Minus 30 minus 2. I'm going to try to avoid using a calculator here. So negative 12,500 minus, I noticed that 75 and 25 make 100. So this is negative 1,000 total. Minus 32. So this will be negative 13,532. Good. So that would be the remainder if I were to do this long division. So if I just want the remainder and I don't need the quotient, then I can skip the long division step and just do this. Okay, so number 2 says, for the following exercises, use the factor theorem to find all real zeros of the given polynomial function and one factor. So basically, what the factor theorem says is that the zeros of a function correspond to factors of the polynomial. So if we were to factor completely, say, the first one, a, then we could get the zeros from that. So I know that, well, I'm given that this is a factor. The problem says, oh, we're given one factor. So I can use synthetic division to do the division and make a factorization. So let's say 2, and then say 2, negative 3, negative 3, 2. You can bring this 2 down, multiply up. 2 times 2 makes 4. Add down to get 1, multiply up to get 2, add down to get negative 1, multiply up to get negative 2, add down to get 0, right? I was told that this is a factor, and indeed, we do get 0 as the remainder. Now, what that tells me is that this quadratic 2x squared plus x minus 1 times x minus 2, this equals the original function f of x. So now if I can factor this quadratic, then I'll have factored the function completely, and I can see what the zeros are. Okay, so I think this one should factor in an easy way. So this should be 2x times x something So this will be a +1 here, -1 here. And if I FOIL that out, I do indeed get 2x squared plus x minus 1. So x minus 2. So now I can set this equal to 0, because I don't really need this anymore. Say, okay, well, 0 equals 2x minus 1 times x plus 1 times x minus 2. So 0 equals 2x minus 1, or 0 equals x plus 1, or 0 equals, run into my other space over here, minus 2. So here, if we solve this equation, I can add 1 on both sides. 1 equals 2x, and then divide by 2, so 1/2 equals x. For this one, I can subtract 1 on both sides. So -1 equals x. And then here, of course, I can add 2 on both sides. But this one we kind of knew already. I'm being a little redundant, I suppose, but I just want to be complete. So we get the 3 zeros of this cubic function. Okay. All right. Am I going to run out of room on the other one? Maybe. Let's do this. I think I should be able to squeeze this a little bit. Yeah, that should be fine. Okay. In fact, I'll change the stylus to be even smaller. Okay, so now I'm going to do the same thing here. I'm going to use synthetic division to divide this binomial into the cubic. A monomial would be one term only. So -1, that's the corresponding root. And then I'll use synthetic division to do the division, just because it's faster than long division. So bring the 3 down. So 3, multiply up, -3, add down, -11. Multiply up 11, add down 6, multiply up -6, add down 0. So 3x squared minus 11x plus 6 times x plus 1 equals the original function g of x. Okay. Now these numbers aren't too big. Maybe I can, through guessing, yeah, I think I see how this factors. We could use the AC method, but if the numbers are small enough and you see how it factors, then you can just go ahead and do that. So this will be -2, 3x minus 2 times x minus 3. Yeah, that's right, times x plus 1. So if I set this equal to 0, I can then factor, well, I'm sorry, I factored already, but I can separate the factors, and we'll put that up here, actually. We'll say that 0 equals 3x minus 2, or 0 equals x minus 3, or 0 equals x plus 1. Okay. So here, I can add 2 to both sides, and then divide by 3. Here, I can add 3 to both sides. 3 equals x. And then here, of course, I can subtract 1 on both sides. This one, again, we already knew, right? I knew that from here, but it doesn't hurt to be complete. So there we go. That is all 3 real zeros of the function. Okay. Now, it was helpful to have this one to get started. And how are you going to deal with that? What if you don't have one to get started with? What do you do? Well, that's basically what the next one is about. This one says, for the following exercises, use the rational zero theorem to list all possible rational zeros for each function. We're not asked to find all of them. We're asked to list all possible ones, and that can be relatively easy or not so much. So we need to look at the first coefficient and the last coefficient. So the hidden coefficient there, the implied one, is 1. Okay, so look at the first coefficient and the last coefficient. Every possible potential rational root will be of the form p over q, and p will have to come from 3. It have to be a factor of 3, and q will have to be a factor of 1. Now, 3 only has 2 factors, 1 and 3. Okay, but you could have -1 and -3 potentially. 1 only has, well, 1 times 1, I guess, and then -1 times -1, right? We might find ourselves being a little bit redundant if we count negatives too many times, but basically every fraction of the form 1 of change colors here. One of these over one of those is basically 3 over 1 or 1 over 1, but then plus minus as well. So basically, we're going to have plus minus 3 over 1, which of course is just plus minus 3, right? There's two possible numbers there. And then plus minus 1 over 1, which is just plus minus 1. So in total, there are 4 possible or potential rational roots to this function. Now, it doesn't mean we found all 4. Maybe 2 of these are rational roots, and then the other roots are not rational, right? They can have a square root or something, okay? So the problem does not ask us to factor this or find all the roots, just the list. It says list all possible rational roots. And this is it. This is the complete list for this one, okay? So not many. This one was relatively simple. Over here, I want to, again, look at the first coefficient and the last coefficient and the factorizations of those. So this could be 1 and 6 or 2 and 3. And then, of course, plus minus. But, we'll handle the plus minus at the end for this example. And here we have 1 and 2. Those are the only possible, the only factors, rather, of 2. So again, every rational root on the list of potentials will have the format P over Q. Again, P always comes from the last coefficient, and Q always comes from the first coefficient. So I could have 2 over 6. I could have 2 over 3. I could have 2 over 2. I could have 2 over 1. Okay, so let's list those out. 2 over, I'll go in reverse order. 2 over 1, 2 over 2, 2 over 3, 2 over 6. Okay, or I could have 1 over 1, or 1 over 2, or 1 over 3, or 1 over 6. Okay, so 1 over 1, and you might notice something here. Well, there's actually 2 things going on, but you might notice one or both of them. 1 over 2, 1 over 3, 1 over 6. So one thing that you might notice is I have a redundancy here. 2 over 2 and 1 over 1 are the same thing. So really, I don't need to list this a second time. The other thing is I haven't said plus minus yet. So our real list is going to be plus minus 2, okay, to cover this guy. Plus minus 1 is this guy. Plus minus 2/3, this guy. Plus minus 1/3, right? Oh, and I just noticed something else. We have 1/3 on there twice, but that's okay. Just cross off the second one. Don't worry about it. So plus minus 1/3, plus minus, oops, plus minus 1/2, and plus minus 1/6. Okay. So there we go. That is the complete list. 1, 2, 3, 4, 5, 6, 12 different options. That's a lot of numbers to check, right? So clearly, since this is a cubic function, it has at most 3 roots. So obviously, this is not the list of roots. This is the list of potential real roots. This cubic, or sorry, not real, rational, sorry, rational. This cubic function might only have 1 rational root, or it might have 3. Okay, so for this one, we're going to find all zeros. And if we have any complex solutions, we'll need to write those in AI plus B form. So looking at this one, I need to first identify the leading coefficient. So for this term, that would be 1. And then I'm going to take these 2 coefficients, the leading coefficient and the trailing coefficient. These I'll use to make my list of potential rational roots. So here, the only factor is 1, so there's not a whole lot going on. But here, I could have 1 in 100, plus minus, of course, 2 in 50. I could have, say, 4 and 25. I could have 5 and 20. I could have 10 and 10. So kind of a long list, right? When I go to make my list of potentials, my P's and my Q's, basically, I'll be making fractions out of these guys with 1 on bottom. So it's basically just plus minus 1, plus minus 2, plus minus 4, plus minus 5, and so on is my list. So plus minus 1, plus minus 2, plus minus, not 3, sorry, 4. 1, 2, 4, 5, 10, 20, 25, Can I squeeze this in here? Perhaps not. 50 and then plus minus 100. Okay. So kind of a long list. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 18. So kind of a lot. When I look at the coefficients involved, just the sizes of the coefficients, I notice that the the negative 100 is a big value, and I'm not sure that a negative number is going to end up being a root. It could, but perhaps not. A positive number could. Something like 1 just isn't going to work. 1 is not big enough. 100, I think, is also too large because x to the 100 to the fourth power. What is that like? Is that 100 million? I think something like that. So I don't think 100 is going to work. Um, maybe we could start with 1. One's not big enough. You know what? Let's start with 2. Let's start with 2. And what I could do is I could find f of 2. Um, or I could use synthetic division to just go ahead and try to divide by x minus 2. So let's do that. Let's say 2, and we'll do synthetic division. So 1, 9, 18, negative 30, and negative 100. And I'm got a really small stylus so that I have lots of room because I suspect we're going to have to do this a couple of times. There's a lot to check here, and maybe we're lucky, but I'm not too hopeful. So bring down the 1. So 1 times 2, that's 2. Add down, you get 11. Multiply that up, you get 22. Add down, you get 40, right? Multiply up, you get 80. Add down, you get 50. Oh, well, okay. And then you get 100, you get 0. Okay, so that divided evenly. Well, that's convenient. Yeah, that was not planned. That was just convenient. So this will be x cubed plus 11 x squared plus 40x plus 50 times x minus 2. This will be equal to the original function f of x. Okay, so we've partially factored. Now what I want to do is I want to focus on this guy here. And I didn't write the leading coefficient just because we're so used to just leaving it off. So I'll put a 1 right there. I need to focus on factoring this cubic. So I'm going to focus on the first coefficient and the last coefficient, and I'll build a new list. This list is no longer necessarily valid because, for example, 100 is not possible anymore. So I need to build a new list. So the factors of 50, this could be 1 and 50, 2 and 25, not 4, but 5 and 10. Right? Those, and then of course, the only factor of 1 is 1. So my list of potential P over Q rational values is plus minus 1, which I still don't think it's going to work potentially, but I doubt it. Plus minus 2, which could work, but 2 I don't think will. I mean, it could, but I don't think 2 will. Oh, in fact, you know what? I can tell right away our next result will not be positive. I'll say why in a moment. So plus minus 5, plus minus 10, plus minus 25, and plus minus 50. So focus on this cubic function. Notice how all the coefficients are positive. If you want to find the number to plug in to create 0, and there are no negatives present, well, the number you plug in would have to be negative, right? Like that 40x needs to be negative to counteract the 50. So maybe negative 2 potentially could work. Maybe negative 5, but the positives just can't. So I'm gonna go ahead and just mark those out. The result cannot be positive. It's got to be negative. Okay. So let's go ahead and try doing synthetic division again. Let's do it over here. What number do I want to try first? Well, definitely negative. Negative 1. Let's go and try negative 1. I think that'll work, actually. So 1, 11, 40, 50. Okay, so I will double check that that's right. Yeah, okay. So I'll bring down 1, multiply up, -1, add down 10, multiply up, -10. Oh, this is not working the way I thought it would be. Multiply down, 30, multiply or add down rather, multiply up, -30. No, that didn't work. Okay, so that's fine. That's okay. Um, well, let's try -2. Let's start with small numbers and work our way up. And I have a feeling that I've made an error, and half of you are yelling at your screen. What are you doing? You didn't do that right. You added wrong or something. Maybe it's 2. -2 rather. Okay. So down 1, multiply up, -2, add down 9, multiply up, -18, add down 22, multiply up, -44. Not quite. Kind of close, but not quite. Okay, let's try -5. If I wanted, I could be erasing these, but I just don't want to do that in this case. I've got all the space in the world, right? Got a whole blank page there. So 1, 11, 40, 50. So bring that down, 1, multiply up, and I get -5, add down, get 6, multiply up, -30, add down 10, multiply up, -50. There we go. Okay, so what this means is that this guy over here, this cubic factors, this is the quadratic factor, and x minus -5, or in other words, x plus 5 is the linear factor. So now we can say that, let's put it here, g of f of x equals x squared plus 6x plus 10 times x plus 5, right? X minus -5 times x minus 2. Okay, we're almost done. We have 2 of the zeros. I guess I don't really have to write it out like this, but I just prefer to in this case because we know that the zeros so far are 2 and -5 so far. So now what I can do is say, well, what would make this equal to 0? Equals 0, question mark. Okay, well, 0 equals x squared plus 6x plus 10. Okay. That I don't think factors in a nice clean way. So let's use a quadratic formula. It's not the only way. We could complete the square, but I suspect for most of you, you probably view quadratic formula as easier than completing the square. So negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay. So negative b will be -6 plus or minus the square root of 36 minus 4 times a times c. A is 1, c is 10, so times 10 all over 2a, which is 2. Okay. So this is -6 plus or minus the square root of, well, that's -4. This is something we've talked about a little bit previously. Not a whole lot. Oh, come on. There we go. 2. That's what I get for not zooming in more. Okay, so what's the square root of -4? Well, that's not a real number because you have an even root of a negative value. So without going into a whole lot of detail right now, this is something that you probably know from a previous course, and if not, you can ask about it. The square root of -4 is 2i. So this is -6 plus or minus 2i over 2, which I can then write as -6 over 2 plus or minus 2i over 2, right? And of course, -6 over 2 is -3, and plus minus I. So the full list of zeros is going to be 2, -5. I'm listing them in the order I found them in. And then -3 minus I. And should pay attention to the directions. Put the imaginary part first. So I minus 3 and then negative I minus 3. Okay, and that should be it. That is all for zeros of that degree 4 function.